Here's a list of the instruments that are currently implemented for both open and laparoscopic surgery. And because the underlying collision detection system is robust, using continuous collision detection, it can be used to develop more instruments in the future. I'm going to show a demo from the simulator of a laparoscopic cholecystectomy. It's sped up 2 times speed. As you can see, the simulator can simulate both the assistant's hand and the surgeon's left and right hand as well. Here the surgeon's using an electrocautery hook, and his performance is sort of dictated by the tension the surgeon's using on his left hand. It really forces the trainee to keep readjusting the tension, similar to real life, to get the ideal hooking and safe electrocautery. Here the surgeon's performing the callus dissection while avoiding the artery. And here the collision detection is fine enough to be able to go between fine structures without the tip of the instrument penetrating the tissues in an unrealistic fashion. And then here we'll cut the artery, showing the blood flow simulation, and then the electrocautery seals the artery. A bit irresponsible surgically, but just to demonstrate. Of the open surgical instruments, the simulator can simulate 3 hands, 2 surgeon hands and 1 assistant hand, and the hands realistically collide with the soft tissues without penetrating them. Here the electrocautery is causing a thermal injury, and one of the most difficult things to simulate was the collision detection in the absence of arresting the surgeon's hand. So, because the surgeon's hand is not limited by hard haptics, the collision detection system has to compensate. Here the surgeon caused some hemorrhage, and they've managed to control it with electrocautery. Demonstration of an open appendectomy. Here the electrocautery is very effective in the beginning because there's adequate tension on the tissues, but as the tension decreases, the electrocautery will become less and less effective, which should prompt the surgeon to regrasp the appendix as a learn while doing point to increase the tension and continue the dissection. As you can see here, there's built-in support for continuous instrument changing, so that the trainee can change instruments on the fly. And with adequate tension, we've reached the base of the appendix and the scissors are cutting, but because the tension is not quite high enough, the scissors aren't cutting ideally. With regards to blood flow simulation, I've developed a novel GPU accelerated blood flow system. It simulates blood flow from an inflow point along the whole path of the organ, and this path can be interrupted by thermal injury or tissue damage. This allows realistic bleeding from the tissue, but also realistic back bleeding from a resected organ as well. Other fluids such as bile can also be simulated through adjustment of different pressures and flow rates. Here's a demo of incising or dividing the common the cystic duct, and here you can see there's bile leaking from the gallbladder, which becomes empty, and then the bile ceases. This continuous leakage of bile from the cystic duct, and here there's bleeding from the cystic artery. However, after increasing the blood pressure, the bleeding becomes more prominent. It's a demo of laparoscopic hemostasis. So some bleeding from the liver bed, and it can be cauterized and the rendering engine changes the appearance of the tissues to be burnt. Of CPU collision detection algorithm showing that the instruments can't penetrate the soft bodies even when they're very rigid, despite a lot of force being applied. And the user's hand not being restricted by any external haptics apparatus. The GPU collision detection algorithm is a novel technique. It handles real-time collision detection between lots of different organs using parallel computing. It's got its own dynamically generated bounding volume hierarchy that's generated on the GPU itself, so it reacts to cut tissue or destroyed tissue. It utilizes continuous collision detection again, so no matter what the velocity is, it can compensate. And is stable even when stacking multiple objects on top of each other or interacting with the previously mentioned CPU colliders. Here's a simple demo of a piece of glass falling on a cube. They're both soft tissues and there's no penetration or jittering. And then there's a more complicated demo showing the capabilities of the GPU collision detection system of stacking multiple objects. Here we're stacking multiple soft body objects with a realistic response and also no jittering or unstable behavior. With regards to tissue cutting, I think that's one of the essential aspects of a surgical simulation, and it's done by deletion of tetrahedra and disconnecting spring links. And it can be initiated with lots of different modalities, whether it's thermal injury, which becomes more effective when the tissue is under stress, high tension, or direct tissue injury from a cutting instrument. This type of simulation makes the dissection a lot more realistic. Once a tetrahedron is removed, the hidden surfaces in the mesh are made visible, and this is achieved through a novel hidden surface removal method. Tissue cutting depends on tissue stress, and I think tissue tension is one of the core principles of surgical dissection. The tissue stress values are calculated on the GPU, and they are saved and used to inform other simulator behaviors. So they affect thermal injury, tissue tearing, and how the instruments interact with the tissues. Here I'm visualizing the stress as more red. So blue is areas of low stress, and then red are areas where the stress are higher. Here's a demo of collision detection and stress. Here you can see the instruments are interacting with the tissues in a realistic fashion. They can't penetrate the tissues unrealistically. And we'll see the effects of tissue stress on the ability of the surgeon to dissect the tissue. With stress being shown in red. I'm going to use electrocautery with minimal tissue stress, and it's very ineffective. However, when the surgeon increases the tissue stress, as in real life, the electrocautery becomes more effective. So this realistic method of dissection enforces good surgical technique. And I feel this is the essence of being able to create a versatile universal simulator.